Good afternoon, class. This is statics, week 7 Wednesday video. I'm going to finish up chapter 5, rigid body equilibrium, working a few extra problems for you. And then I'm going to go through the solution to exam 1. It's posted on Canvas, but I do want to make a few comments on each of the problems. Make sure we're on the same page in terms of what the problems actually ask for in there. And so let's go ahead and work a few problems in chapter 5 then. So here's the first problem we're going to take a look at. We have a beam that's actually supported at a pin, which will have an X and Y component of reaction. There's a strut CB, and we'll know the reaction in a strut is going to be just a line of action along the strut, and this is going to be in compression. And then we have two vertical loads, 600 newtons, 1 meter from the end, and 800 newtons, that's 1 to 4 meters from the end. And then there's an applied moment of 800 newton meters. So what we want to do is draw the free body diagram. And so we'll do that right here. And so I will have reaction A sub y. And I'll show my A sub x this way for now. And then we have the strut out here. And I know that's going to be in compression. And that's BC. And I have two loads, 800 vertical load of 800 newtons and an applied moment of 900 newton meters. I'll go back to this slope on here in just a minute. And then I have this 600 Newton force acting at a distance of 1 meter. And then it's another 1 meter to the strut, and then additional 2 meters out to the end. And what we need is a slope on this strut. And if you look at this, we have 1.5 meters vertical and 2 meters horizontal. And I'm going to show you, I'm going to come over here. Well, I'll just show you over here on this one. I'm just going to draw this strut, show you what I'm going to do with this. Again, I really do like slopes because it saves having to calculate an angle and then taking a function of that angle in order to do this. So so we have 1.5 vertical and 2 meter horizontal. I can do this, you know, and sum the squares and take the square root and so on. But what I also do is recognize there's a sort of a proportion here. And what if I multiply these both by 2? A lot of times you can see this in our problem. And so this gives us a slope of 1.5 times 2, 3, 2 times 2 gives us a slope of 4. So this is a 3, 4, 5. And there's no calculation that you have to do. You can you just multiply by 2, it's 3 and 4, 5. So this slope then is a 3, 4, 5 slope. Okay. And as I go about solving the problem, recognize I have two unknowns here. So what I need to do is sum moments about a equal to 0. That takes care of the fact that I don't have to include additional unknowns in the equation, and I can solve for the one unknown that we're looking at. And so I have the force in BC, and we need both. I'm going to do the horizontal. I'll show you the horizontal component. Well, let me just go ahead and say that horizontal component through here is going to pass through this support, and so horizontal component won't create any moment. It passes through the support. The only component that's going to create a moment is going to be this vertical component, and it's 3/5 of BC. So it's BC times 3/5. It's the vertical component. Moment arm is 1 plus 1 is 2. Okay, and again, this is going in the counterclockwise direction, which is positive. And then minus the 800 newtons. Well, let's do this minus the 600 newtons times 1, and this will be minus 800 newtons times 2, 3, 4. And then we have the 900 Newton meter moment directed at the end. And that's going to be minus 900 Newton meters out here at the end, and all that's equal to 0. So very quickly we can solve for BC. Then let me show you this out here on the calculation. So we have the BC, 3/5 of BC, which is the slope. Okay, I showed you how to get that slope out there. So it's 3/5 BC times its moment arm, which is 2, and then minus 600 times 1, and then minus 800 times the 4 out here, and then you have the applied of 900 Newton meters, which is 9 minus also. And so BC, I want you to do the calculations then, is going to be, well, here's what it runs out on: 3,916.67 kilonewtons. And so what we want to do is write this with 3 significant figures. So this will be 3.92, moving the decimal out there, kilonewtons. So this is BC. And then what you do with that, you can sum forces in the X equals 0. Okay, and so when you sum forces in the X equal to 0, you have the A sub X. I showed that as positive. And then you have the X component of the strut passing through here. The X component of the strut then is going to be 4/5 of BC. And I'm going to go ahead and, since I'm doing the calculation, I'm going to use BC as the what I found in the using the calculator, which was 3,916.6. Okay. That's going to be equal to 0. And so A sub x then is equal to 3.13 kilonewtons. And in fact, that is the correct answer. Actually, it actually comes out to be negative. I want to show you something with that. That's a negative 3.13. With the way I've drawn it this way, this is positive, and this is positive also. So this actually comes out to be negative 3.13. So A sub x is minus 3.13 kilonewtons. The significance of a minus sign is the fact that I chose my direction incorrectly to begin with. So the minus sign in an answer, what that means is the original direction that I chose for A sub x positive is incorrect. The direction is actually in the negative direction. So what I'm going to do is write this. I would write the answer as A sub x is 3.13 kilonewtons. And then I'm going to show the arrow going in the correct direction. And what I wouldn't do in this case is go back up in my diagram and change the direction, because that's how I solved. But I do want to indicate that the direction actually is directed to the left. So I'm going to put that arrow in my answer, indicating that in fact A sub x is going in the negative x direction and not as I originally drew. You'll see some problems where you may not really know what the direction is beforehand, and so you can choose positive if you want to. If the answer comes out negative, then it's this. Now, what I could have done, and looking at this, I say, well, the only x component is from this force, and it's directed in the positive x direction. So A sub x has to be in the negative. So you could have drawn this originally in the negative x direction, and your answer would have come out positive, and you wouldn't have to do any changes. But sometimes you don't know, and it's just easier just to do both positive, and then the answer tells you if you're wrong in terms of showing that as a negative solution. Okay. So let's take a look at this second problem that I have down here. It's an interesting problem. The floor crane and the driver have a total weight of 2,500 pounds. This is acting at the center of gravity, which is located here. This distance from this rear wheel. This is actually a real world problem that you're going to be looking at. So it's 2,500 pounds weight total, acting at the center of gravity. And what we want to know is the largest weight of the drum that can be lifted without causing the crane to overturn when its boom is in this position. Okay, so it's at an angle of 30 degrees. It's an angle of 30 degrees with the horizontal. This is a real problem in manufacturing facilities and store facilities also. If you have a crane that's oriented this way, you want to determine what the maximum load is on this crane, and I'll talk about maximum load in once we get this done. And what you don't want to do is have this crane to tip, and it's going to tip about this front wheel and lift this back wheel A off the ground. So what's the maximum load where this won't occur? Again, we got a fairly complex structure that we're looking at. And so the question is, what do we want to do with the free body diagram to make it look or to simplify the problem itself? And so we have to construct our free body diagram. This is going to be not quite as simple as the other ones because we have to show some exactly what's going on in here. So I'm going to, I'll draw the base where the wheels are like this as we're looking at it. I'll drive this, indicate this, I'll simplify this area where the driver sits and do something like this. And so I can attach the crane, and it's going to extend past the end. And what we're going to do is have the weight W, and I've got a front wheel out here that will be on a wheel. We know only has one support direction that's perpendicular to the surface, and that's at point B. And so we'll call this B sub Y, and then over here at the back end of this we have an A sub Y. So I have an A sub Y here. This angle is 30 degrees. And we have this length up here situated from the center of gravity out to the end. Total is 15 feet. And it's acting at an angle of 30 degrees. So that's 30 degrees right here. And we want to know what weight is tipping. Well, we have three unknowns. None of these are in the X direction. They're all in the Y direction. The load is in the Y direction, weight. So the question is, we have three unknowns, but the only equations I have are a moment equation and a sum of forces in the Y. I only have two equations to solve for three unknowns. So that poses a problem. Okay, here's where this problem is unusual. You have to use a little bit of judgment to look at what is happening in this situation when the crane is just getting ready to overturn. So when this starts to just overturn, what happens to this reaction here on this wheel at A? Well, this wheel is just starting to lift. It's on the verge of lifting. And so at that instance where it's at the verge of tipping, this is at the verge of lifting. And so this reaction actually is equal to 0. There is no load just as this thing starts to tip. Okay, so actually we only have two unknowns, v sub y and the weight. Okay, so we can now solve. I'm going to take moments about v sub y. Equal to 0. I have the weight acting down at 2,500 pounds. So I've got this weight, got that directed here. So this is my 2,500 pounds. I have the horizontal distances for each of these dimensions through here. So it's 9 feet, 8.4, 8.4, 1.4, and 0.2. So it's 0.2, 1.6, 8.4. So it's actually 9 feet then, all the way from the end of that, from v sub y out to that load. So this is (8.4) plus the 1.4. So this 1.4 is the center of gravity, 8.4 is out to here. So this is going to be 9 total dimension this way. Okay. So from this load here, this is going to be 9. It's 2,500 times 9. Actually, it'd be 4 plus 4, 8. 9 points, be 9.8 feet. 8.4 times plus 1.4. 9.8 feet. That's 9.8 feet. That's positive, and then minus W times the distance out. What we'll do is convert this 15 to get that distance, and then we'll subtract this distance from it to get the distance out from this wheel here out to this distance here. So I'm going to convert this 15 plus 3 feet out here to this mark here. So it's 15 times the cosine of 30 degrees minus the 8.4 here, which gives us that horizontal distance from here to here. And then that's equal to 0. And you end up with a weight then equal to 5,337.25 pounds. We want to write this to 3 places, so it's going to be 5.34, and we use KIPS in the UPS, our American System of Units UPS, which would be 1, 2, 3 to here, so this will be 5.34 KIPS. So this is the maximum weight. This crane would not be rated for that weight. Depending upon the factor of safety you want to put on there, you would divide this by 1.5 or 2, probably, and that would be the maximum weight that you would carry out here. You want to always have a factor of safety. Probably this is a pretty accurate calculation, so you'd have it probably use a lower factor of safety on there. Again, that will vary with the angle, okay, that you're carrying it. But if it's just moving certain pieces of equipment or material around, this may be something that's fairly constant. Otherwise, you'd have maximum capacities for different angles that you're looking at. Okay, that's the maximum weight. You'd probably use something less as you go through the calculations. This is bulkhead AD. It's a bulkhead because you're retaining water. If this was just a soil that you're looking at, you're looking at a retaining wall. Okay, so without the water, this is a retaining wall, and we've all seen retaining structures in there. I don't know if you realize this, but there is a pressure in soil, varies from 0 out to some maximum at depth. So there is significant force on retaining walls, wanting to push the retaining wall off. And in my consulting business, I've done a lot of analyzing and correction of failed retaining walls. If you get water back behind here, this water causes an additional pressure. And if you don't put weep holes along the bottom to drain that water out, you could actually enhance the potential for failure by adding this additional water pressure behind the retaining wall. That's why you tend to see weep holes along the base to get rid of excess moisture, let it drain out. Okay. And so as a bulkhead, there's water in front of it, and water again has pressure. We know that if you're divers, you know pressure increases significantly deeper you go. So there's a linear pressure from 0 down to 118 kilonewton meters. As with soil, there's a pressure from 0 for 300 kilonewton meters at the base. In addition, you can place in here these structures which are anchors, soil anchors. Okay, call them ground anchors. They're both appropriate names. So these are ground anchors that would probably be positioned linearly along the length of the bulkhead to provide an additional reaction against the soil pushing out. Another problem you can have too is if you put parking on top of here, or you build something else on top of the soil at this particular end, it adds increasing weight here and pushes out. So anything we analyze here is just this point in time, but we imagine it's occurring across the length of this bulkhead. And so this would end up, actually, you can figure out what the spacing would be depending upon the length that you have. So we're going to assume AD down here is a pin connection, so it's free to rotate. Okay, typically that's what we do, is they're going to be free to rotate. Otherwise, you could actually have some real issues up in here in terms of failure conditions if you don't allow that. And we want to find out what the pin reactions are. We want to find out what this ground anchor tension is going to be in here, what that needs to be. And for that, once you have that, you can actually design this ground anchor, a length and maybe the size of the ground anchor itself that you're looking at. Okay, so that's the problem that we're facing in here. So, free body diagram. You know, I think I can draw. Let me just draw this out here, the free body diagram. So you have the retaining structure. You'll have a A sub X and an A sub Y. I don't know which direction the A sub X may go, so I'm just going to do this. You have a force here. It's a triangular load. Okay, so the triangular load is going to be 1/2 base times height. And it'll be acting 1/3 the distance up here. Okay, total height is 6 meters, so it's 1/3 up or 2/3 down of the. So I'm going to have a horizontal force here, and this is it's going to be area of this triangle, which is 1/2 the base, which is 110 times the height, which is 6.5 meters. Okay, see what we did? 1/2 base times height. We've done the triangular loading previously, so it's just 1/2 the base. The base is actually 310. So it's 310. Height is 6 plus 0.5, so it's 1/2 310 times 6.5. And this is 1,007 kilonewtons. 1,007.5 kilonewtons. And then you're going to have the water pressure. And the water pressure is acting 4 meters high, so the water pressure is over here. And again, it's 1/2 the base, which is 118 times its height, which is 4 meters. And so it is going to be I've got that calculated there. It's 236 kilonewtons. So this is 236 kilonewtons. Okay, and then you have the anchor force in the anchor up here. So we're going to be taking moments about A. So this distance then is 2/3 the 6.5. And that is 6.167. 6.17 distance up here. And for the water that we have there, it's 236 and its distance is 3.33. So this distance is 3.33. And so we can do the sum of the moment. So the moment's about A equal to 0. I've got the 1007.5. This times its moment arm, which is this distance here, 0.167 or 2.167. This distance up to here. It's acting in the causal moment in this direction, counterclockwise, which is going to be positive. And then we have the minus 336 times its moment arm of 1.33. And that's all equal to 0. Well, you have one other, which is our force up here. And I'll put this down here. So minus F times its distance. And its distance was 6 meters here. And that's all equal to 0. And we solve for F is going to be equal to 311 kilonewtons. So we have this force, soil, we have the water force, and we have this anchor force up here, and its distance up is 6 meters. We solve for F, 300 kilonewtons, and we sum forces in the X then, and we can solve. We've got the A sub X positive. We have the water pressure, which is the 300. $236 there. So we have the water pressure, 236. We have the force of 311. Equals 0. Well, then you have the minus what is it, minus 175, minus 1075 equals 0, and a sub x then is going to be equal to 460 kilonewtons. There's some forces in the y equal to 0. A sub y minus 7848. This is the bulkhead has a mass of 800 grams, 800 kilograms. So there's an 800 kilogram mass here times the 9.81 gives you minus 7848 kilonewtons. That's the mass of the bulkhead equal to 0. And so a sub y then is equal to 7.85 kilonewtons. Okay, so this bulkhead massive 800 kilonewtons or kilograms right here. Bulkhead has a mass of 800. So 800 times 9.1 gives you the kilonewtons, and you can solve for a sub y. So you have a sub x, and you know, excuse me, then you know the force required for that anchor, which gives you probably the size and the length that you need for the anchor. The farther you drive it in, you get more friction here, and then you go along the retaining structure, and you can actually determine the spacing you need, because you can be working in a third dimension to get total load in a three-dimensional sense. You can figure out what spacing you need for those anchors along the length of that bulkhead. Okay. I'm going to show you one additional problem. And this one worked out. Boy, this is an important problem that will take us into the next chapter in particular, when we continue on with this analysis of beams and stuff as we go through. So again, we have a simple beam, A and B. We'll talk about reactions next lecture a little bit more. We have a load that looks like this. We see it's uniform up to a particular point, 4 feet, and then it starts to be a uniform load that is increasing along a line. Okay. So we have really two areas, and the way I would approach this is to make this a rectangle down here that's going to be 4 plus 3, 7 by 200. And then I would have acting at the center of gravity, and then I would have a triangular load here, which is 1/2 the base, which is going to be the 3 feet, times the height, which is 400 minus 200, which would be 200. Okay. So this area up here is 1/2 the base, which is 3 times 200, which will be 300 newtons. This is 4 and 3 is 7 times 200, which is going to be 1400. So the rectangular load is going to be 7 feet times the 1400, which will be 2800 newtons acting down. And this one will be the 1400 is going to be acting at the center of this rectangular load. So here's the 1400 newtons, and it will be acting 4 feet over. And then the 300 newtons is going to be acting 2/3 this distance. And what we do is this is 7 feet, so it's going to be acting over 3.5 meters here, which is what I have here. This will be acting at 2/3 this distance. So it's 4 plus 2/3 of 3 is going to be 2. So this is acting at 6. So what I've done then is I've converted this uniform loading and this triangular loading part on top of it as 2 loads, 400 Newton acting at 3.5 meters, and 3000 Newton acting at 6 meters, its center of gravity. And you do a simple moment about either one of them. To start with A. Okay, simple moment about A, you get B sub y. Simple calculation. And then you can sum forces in the y, you get A sub y. If you want to check, okay, sum of forces in the y, get A sub y. If you want to run a check on this, take moments about B, okay, and you should get what you found for A. That's a check you can do on, one of the checks you can do on an exam. I'll point out others as we go to different problems in subsequent chapters, but there is a check that you can do most times on calculations. And so you can use a different moment equation and see that you get the same answer that you calculated using sum of forces. You need to be able to convert these types of loadings into concentrated loads acting at the center of gravity of the load itself. Okay. And go through that ends our discussion really on chapter 5, showing you some more example problems. Go through the exam briefly. I want to make a couple of points with the exam. This is the solution. I have the solution posted on Canvas. This one was a very simple problem. Just wanted you to determine the magnitude of the resultant force and direction measured counterclockwise from the positive x-axis. So what you're doing is you're just finding the x and y components. But some of you made a mistake with this 30-degree angle, and instead of using in the sine of forces in the x, instead of using the sine function, which is actually opposite this case, and be in the x direction, you use the cosine function. And the cosine function would have actually given you the y component. And so when you did the y, you used the sine function instead of the cosine function. And the message here is, regardless of the examples we do in class, you need to make sure you are representing your sine and cosine function appropriately with how the angle is measured. And again, using the slope makes it a real easy calculation too, as a 3, 4, 5, then using the slopes for the other angle, the 85. 4, 5 here, and 3, 5 for the y. It's 3 in the y direction, 4 in the x direction. So 4, 5 for x component, 3, 5 for the y component. Again, keeping your pluses and minuses. These are both minus. This is plus minus this way, and this one is plus plus for both of them. And so you end up with a resultant of 546 newtons. Again, we calculate the angle theta, and the angle theta that you're looking at when you calculate this way is going to be 72.64 degrees, and we want it counterclockwise with the positive x-axis. And so what we need to do, since this is the angle we're calculating, is this is 180, 270 minus that angle gives us 100 and gives us this angle here, which is 107.726, or 100. Yeah, 253. And so what you need to do is just write it in 3 decimals as you go through this. 253 degrees. Okay, straightforward. $253. This one, we want to determine the magnitude of the projected component of F along cable BA. So we're talking about BA here, B to A. So you got your signs wrong because you want A to B, it's B to A. And F is given as a Cartesian vector. It's just a dot product, which is a multiplication of the I, J, and K components. It gives you a scalar. And then extra credit, express the component as a Cartesian vector. So what you have to do, since it's along BA, you just need to get the unit vector. Okay, that's what we're going to multiply by. Unit vector, whatever line you're looking at. So BA, you're just going to get the components, which is going to be a positive 6i plus 1j minus 2k. And then you're dividing by the square root of those squared, and so you end up with 6/64, 1/64, and 2/64 I. And so this ends up being the unit vector. And so the projection scalar FBA is going to be the Cartesian vector times the unit vector. Here's the Cartesian vector acting on BA. Cartesian vector. This is the unit vector that we just calculated here. Dot product, I times I, J times J, K times K. So I did this here, keeping track of the signs, end up with scalar quantities. And so the F projection on BA is 94.2 newtons. And to write this as a Cartesian vector, you just take this scalar quantity, and you've already done the unit vector up here, times its unit vector. And so you get this as the Cartesian vector. Okay, so it's just the products of the dot product. So it's I, J, J, K, K. This is what I did. I components multiplied, J components multiplied, K components multiplied. 3 scalar values, add them together, you get a scalar quantity. Extra credit is just the scalar quantity times the unit vector, which you already did right up here. You already had the unit vector. Multiply those out, and this is the unit vector for the projection. And it's a pretty straightforward problem with dot products. And again, it's not an inconsequential problem. There are many times in design, particularly in mechanical and aerospace, where you want to know the force acting on a particular axis system or another particular member where a force is applied for design purposes. And this dot product will give you that force acting on some other line of action, piece of a component or just some axis that you're looking at trying to do. Okay, third problem. You have a 100 Newton crate, Newton crate suspended vertically. By 3 cables, A, B, and C. And these are rods, so the forces are going to obviously be acting along those rods. Develop 3 equations that you would use to solve for the force in each of the 3 rods. So the first step in all the problems is to write these as Cartesian vectors. You need the unit vectors. Again, you're looking at each one of these, OC, OB, and OA. You're just looking at the components. I have the components here. There may have been some sign issues. I don't quite remember, but you're going from here, O to B, O to A, and O to C, and you get your plus and minus directions here. So I have the components. And then to get the unit vector, again, it's a square root of some of the squares of the components of the IJK. And so you have the unit vectors, OA, OB, and OC for each of these. Then to come up with the equations, you're just multiplying each one of these by the unknowns, FOC, FOB, and FOA times its unit vector. So that's very simple. Okay, once you have the unit vectors, everything else is, you're just going through this exercise of putting the unknowns out and multiplying together. So you have this for FOC, here's FOB, and here's FOA. Okay, as you go through this. Okay, so FOC times its unit vector, FOB times its unit vector, which we got up here, FOA times its unit vector, just real simple. I mean, there's no calculations that you have to do once you do the unit vectors. And then to get the three equations, you add the I components equal to 0. You add the J components equal to 0, and you add the K components equal to 0. And that's all you needed. Okay, so you just add the I, J, and K components together. And those are the three equations. You set them equal to 0. And that's all you needed. And to solve for extra credit, solve for a force or one of the forces. And if you'd have solved for one force, you'd have gotten extra credit, and probably more, you got more extra credit as you do that. And what I did, I put an additional calculation for an unknown in your Canvas. It appeared underneath the solutions to the problem, because the solution that I posted with the solution to the exam was in upside down, and you couldn't see it. So what I did is I did another calculation and posted it on Canvas. And you can go through this yourself. I added I and K together equal to 0, and that got rid of I saw this, if I just added, it would get rid of the FOC, so I'm left with this. And then I added J and K and figured out what I needed to multiply 1.492 to get rid of another unknown. And so I could solve for FOB in terms of FOA, plug back in, and solve for FOA equal to 36.6 newtons. So I guess to simplify, if you have something like this, where you can just add, you get rid of an unknown. Here I had to multiply by a factor here to get rid of another unknown, and a couple other equations I'm looking at. So I get FOB in terms of FOA, and then I plug it back in to my other equation, and I can solve for FOA. Okay, so I can plug it back into this equation that I have up here in FOA. And then once you have that, you can go back in and solve for the other unknowns fairly quickly. I just wanted to show you that. And I did post this in Canvas. It's an extra posting with the solution. So this is the fourth problem. We're given a weight hanging over this pulley of 250 kilograms. And what we want is the forces in AB associated with this mass out here. And you just draw your free body diagram. You want to know what this weight is also to support this load. And we know this pulley system, whatever the force is here, is going to be the same force here. So when you draw your free body diagram, the only unknown that you have is the W1 and then the force in AB. You can work this with the mass and then convert at the end. I just went ahead and converted the mass to a weight 9.81. So it's 2,453 newtons, and I wrote this as 2.45 kilonewtons. Okay, so let me do it. So this is the free body diagram. This is what I was looking for first. And the slope on this, we don't have an angle. It's 3, 4, 4 here. So this is a 3, 4, 5 slope. Typically, if you're given the dimensions, you're going to have the slope given to you also. This one is a 1-to-1 to square root of 2. It's a 45-degree angle, if you recognize that too. This is 400, 400, 1-to-1 square root of 2. I just used the slopes again when you do that. And then where are you going to start? Well, you know, one of these x's, you could do x's, probably you need to do that first because you need to get the y component to do the weight 1. So I did sum of forces in the x equal to 0. So it's 3/5 of the 2,453 newtons. Okay. Minus 1 over the square root of 2 AB in this direction equals 0. You solve for AB very quickly. 1,471. So 0.707 AB, 1,471 AB then is 2.08 kilonewtons. And then just some forces in the y minus W1, and then this would be in the y component then over 3/5 of the 2,453 newtons, and then 1 over the square root of 2 for the AB that you have over here. Okay, that we solve for. And so you get the weight is equal to 3.43 kilonewtons. It's 4. This is the extra credit problem. Thought this was, again, is pretty straightforward. 5 kips. That's the only force that we have. You want to solve for F1 and F1 and F3. This is the only force in the y direction. So you sum forces in the y. It's this equation here. Okay, again, so this is a sine function for the F3. F1 is also a sine function of its 60 and minus 5. So you have an equation with F1 and F3. and then you sum forces in the x direction. These are going to be cosine functions for F1 and F3. It's just a substitution back, and you can substitute any way that you want to. And I just found F1 is equal to 1.73 F3. And then I substituted, this is equation 2. I just substituted that back in equation 1. With that substitution, solve for F3 is 5 kips, and then F1 then is 8.65 kips back in here. So it's just a matter of writing the two equations, two unknowns, and it's a simple substitution back in here. It's extra credit. And that concludes our brief review of the exam. Again, and this solution is posted on there. So that can conclude the chapter 5, rigid body equilibrium. I'm going to start on chapter. Well, actually, I'm going to do probably on Monday. I'm going to finish up with a 3D problem. We need to talk a little bit about 3D in this chapter, and then we'll go to the next chapter also during the same lecture after we talk about the 3 dimensions. And I'm going to show you a little bit different approach to the 3D if you can recognize certain conditions, which could simplify the way you solve certain 3D problems. We'll go through those examples on Monday, and probably get ready to start for the next chapter also during that lecture on Monday. So we'll sign off for now, and I will see you again next week.